Okay, so good morning, everyone, and thanks for coming to this morning's session. So you have 2 talks, and then a break, and then 2 more talks, and then lunch. It's a very brutal schedule. Okay.
And lunch?
2 talks, a break, 2 talks.
Okay. That's a new concept today.
Okay. So the first speaker is Michael Luby, I'm sure you all know, who's from Qualcomm. And he's going to talk about coding theory for scalable music delivery, which I think you've been working on for quite some time.
Forever.
And I thought I'd be, we're supposed to be practice to theory, so I thought I'd do some real practice. But I will do, everything should be accessible to everybody today, so I'm not going to do anything very difficult at all. In fact, I like this thing that Amena said yesterday. Who was it? Yes, he said your goal is not to cover a lot of material, your goal is to uncover a little bit. So I'm going to probably uncover a very little bit, but I will give you sort of a kind of a practical perspective. So this is kind of where my world lives. There's application layer erasure coding complements traditional error coding. So I think a lot of people, you probably know this, everybody in this audience knows this picture very well. When people talk about forward error correction, often what they're thinking about is really physical layer error correction, error coding. And that's the vast majority of current use of FEC. It's probably what you're, not only you guys, but everybody else is familiar with. It's typically applied at layers 1 and 2, and it's usually performed in hardware. You have physical layer forward error correction. What we're talking about today is really erasure coding. It says relatively new. I don't know if it's all that new at this point, but it's still not nearly as popular as error correction, that's for sure. It doesn't replace error coding in any way. It's kind of a layered thing. They're very complementary to each other, just as I'll describe on the next slide. It's typically performed in software, and it's called application layer forward error correction. So just so everybody's, really simple stuff. This is how it really works. You've got packets, IP packets typically, and you have a header on there, an IP header, but you also have an FEC header that describes what's inside the packet. So if you have corruption when it's sent over the network of any kind, what happens is the lower layers discard it, and it's erased. And so what you get is these set of packets with the header, and you can identify what's in the packets from the packet header, and that's why it's really the erasure channel is relevant. Okay. And then the idea behind application layer erasure codes is, as you all know, is you have source data, you break it into source symbols. Sometimes you have multiple source symbols per packet, sometimes you don't. And then you encode it by generating repair symbols. You packetize it, you transmit it, you depacketize, this is a step where you understand which pieces of the data, which symbols you actually receive, so that's why it's an erasure channel. And then you recover the original source data by erasure decoding. So this is probably, this kind of, for me, explains the relationship between application forward error correction and physical error FEC, at least in sort of a broadcast channel, which is basically what I'm going to be focusing on today. So the application layer FEC provides packet protection over small to large blocks. It has very flexible time diversity and a flexible amount of protection because it's at the application layer, right? So you can encode and decode large quantities of data. So flexible time diversity of protection from sub-second to hours, potentially, of protection. On the other hand, the physical layer FEC is actually doing something much more difficult. It actually has to find the errors. It doesn't know where the errors are. It has to try to correct those and discard the corrupted packet with high reliability if it's actually got uncorrectable errors in it. And this is typically over a small interval times, sub-second, typically. And it's a fixed amount of protection because the implementation of all that is in hardware or firmware. So here's kind of how they work together you have some signal to noise ratio. And actually what typically happens with a physical FEC is that it kind of has this brick wall where above this it corrects and below this it has to discard things it can't correct, right? And so the basic idea behind the erasure coding is to encode at a higher level, and you break up your packet stream into source block and source packets and repair packets, and then when the signal is bad, you lose those parts, but when it's good enough, you receive those packets, right? And then the idea is that you lose a little bit of your rate, but what you've done is you cleaned up the channel. So you actually take something that has maybe a potentially high error rate and cleaned it up into something that has a much lower, potentially even zero error rate, ideally. So, for example, in this, it's kind of an old example here, but you had a 5.3 megabit per second channel with a 14% packet error rate, and you've cleaned it up to have a reduced rate 4.3 megabit per second channel, but now your error rate is essentially zero. Yes?
Can you comment about feedback in these channels?
So there's all kinds of networks, channels. In the ones that I'm going to be talking about later, there is absolutely no feedback from anywhere. Actually, there is, and there will be a little bit, but it's sort of indirect, and it's on a different time scale, right? It's not at the level of the networking kind of layer. So what this kind of refers to is a case where you really have a broadcast channel. You don't have you're not working over the internet.
So there's no ACK acknowledgement?
Absolutely not.
And there's no TCP acknowledgement either?
This is not TCP.
Okay.
UDP. Yes.
Just from the general way you describe it, it's analogous to concatenation, I guess. I mean, your application layer is kind of, you talked about it cleaning up the physical.
Yes. Yes. Yeah, and it's kind of like one. But it's kind of good to keep those layers. So people have sort of thought about, oh, why don't we try to combine these two things together, right? Do the erasure and the error correction together. And in theory, that's a great problem to work on. In practice, there's all kinds of reasons that just will never work. I mean, maybe it will work in some future version of some system. You have to redesign the whole thing. And in fact, there's good principles. You know, I have actually, as I'll describe a little bit later, I've worked in the standards area quite a bit, not that much, but a little bit. And I understood from this that there's really good reasons that there's layers in the architecture, because you can kind of take out one and replace it with something else without disturbing everything else. And if you don't have that kind of architecture, you kind of get stuck into this monolithic thing and nothing can ever change.
Yeah.
Okay. So I think everybody in this audience knows what a fountain code is, so I'm not really going to go into that. But essentially, it's just you can keep generating. It's a systematic fountain code has the property that the original source is part of the encoding, but you can generate repair symbols as long as you want, essentially, without really any time or complexity penalty or anything like that. So it's kind of an on-demand code. You can just keep asking for more symbols and you can get them. And I think you're all probably familiar with LT encoding, so I'll just kind of flip through these slides. But essentially the idea is it's very simple, right? You just take random linear combinations of source symbols in the simplest format of it, and you XOR them together, and that's what you send in the non-systematic version of it. And it's really the whole idea behind how it works and why it works is behind this probability distribution, which is how you choose these degrees with certain probabilities. So for example, you choose the degree to be 2 with probability 50%, probability 3 with 17% in this example, and so on. And the whole idea you're doing that is to make sure with high probability that belief propagation decoding works and recovers with the minimal amount of reception, so you don't need to receive many additional packets beyond the size of the original source block to recover with high probability. And this really, the belief propagation part is just to make sure that the decoding complexity is equal to the encoding complexity, which is equal to the number of symbol operations you have to do with belief propagation decoding, is equal to the number of edges in this graph, right? You can see by how it works that every time you do a belief propagation decoding, you're dealing with one edge, you're removing that edge for the next step, and you just keep going. So as you go along, you can see that the total complexity is proportional to the number of edges in the graph. And that's both for the encoder and decoder. So I'm not going to go through any of the theory or anything. As I said, I'm going to make this talk really, really simple, and I think probably a lot of you know more about the details than I do. But this is one intuition that maybe you have or have not seen, so maybe this one is worth thinking about a bit. So there's this degree distribution which says what's the probability that you choose an encoding symbol of a certain degree. And the intuition about why you pick a certain degree distribution is, well, at some point the encoding symbol releases. And what does it mean to release? You've recovered all of its neighbors but one. So it's got exactly one neighbor left, right? If it's degree D and you're kind of decoding and its neighbors are the ones that are being decoded are random, you expect to use that encoding. It's usable when a fraction of something like 1 over D of the source symbols are remaining, right? Because that's the kind of the point where you've kind of recovered all but one of its neighbors, right? So it says it's kind of useful when approximately 1 over D of its neighbors are left. So if you kind of dedicate the degree D guys to cover the interval between the D minus 1 and D, you get a 1 over D times D minus 1 length interval, right? And that sort of says that's what the probability of choosing a degree D should be. So that kind of gives you some intuition why this ideal Soliton distribution has this probability of degree D is 1 over D times D minus 1. It's just the interval of space between, for example, of degree 3, it's this interval of probability between 1/2 and 1/3. Because intuitively, you're going to use degree 3 guys to recover here. You're going to use degree 4 guys to recover here. And this is how much you need to recover, and so on. So it's an intuition. It turns out the reality is a little different. So, you know, for example, 1/2 has got some slope to it, and all these polynomials. But nevertheless, when you add them all up, it does turn out to be uniform release distribution. And here's one other simple, very simple thing about choosing from the Soliton distribution, which I don't know. I kind of like it because it's about as simple as you can get. One way to choose from is just choose a random number between 0 and 1 uniformly. And then just take the inverse of that and round it up. And if it's bigger than 1 over k, you make it equal to degree 1 guy. So that's a very simple way to choose from this. And there's some other interesting things you can analyze from that. OK, so let me shift gears a little bit and go to much more practical things. So over the years, we've worked on these so LT codes, and then we had Raptor codes, and then Raptor Q codes. So these are codes that have been standardized in the various standards groups, for example, the IETF. So the Raptor codes were the first. This is this RFC 5053. RFC stands for Request for Comments. And that code has been also adopted into a variety of other standards around the world. These are systematic fountain codes. They have linear time encoding and decoding. They have very good recovery properties, like a random GF2, and pretty good flexibility. They specify up to 8,000 source symbols and up to 65,000 total encoded symbols. And then the newer generation are these Raptor Q codes, which are also systematic and have very fast encoding and decoding. And they have really good recovery properties, like a random code over GF256, even though they are linear encoding and decoding. And we've specified, standardized these up to around 56,000 source symbols and essentially an unlimited number of encoded symbols, more than you would actually ever really need. So I'm not going to go into the details of this, but these are kind of the major technical features that are involved in these codes. So only one small component, hi Ellie, is the the LT code part, which was incorporated as an essential feature of the Raptor RFC 5053. But that's not nearly enough, right? Because if you just do the belief propagation with LT codes, you're not going to get anything that's really practical. And to be honest, it drives me crazy that people still out there in the research community still write about LT and compare their code against that as if though that's the best one out there. It's like,
That's why they're
So there's a thing called precoding, which is, you add LDPC and actually have an HDPC layer as well. And that was all in the Raptor RFC 5053. That actually makes sure that it really has it's invertible with high probability. And then it has something called inactivation decoding, which essentially means you're doing Gaussian elimination. So you decode if you can, right? So there's no, if it's decodable, you don't get stuck just because belief propagation gets stuck somewhere. You keep going, and you kind of solve the thing when it's solvable, no matter what. So the probability that it's full rank is exactly the probability you're going to decode. And then it's also incorporated this systematic construction, which includes the original source. I'll tell you, in the original form where we tried to propose these codes in 3GPP beyond the IETF, we ran into problems because we only had the non-systematic construction at that point. And then all these companies came forward and said, no, we demand that any code we're going to accept has to be systematic. And so that led to a rush of research, which led to this systematic construction. And then, so those are all in 5053. Going beyond that, in Raptor Q, it has two additional elements to make it really strong. One is obviously the incorporation of larger finite fields, but those are sprinkled in there in a very sparse way. So really, it doesn't affect the complexity. There's only a very few equations that are over GF256. A vast majority of it's still over GF2, so the encoding and decoding is still super fast. But it really significantly reduces the reception overhead, and the error curve is much, much, much better. It also, to sort of work in conjunction with that, there's this idea of permanent inactivation, which really reduced the reception overhead significantly as well. So if you want to read more about this, there's this monograph that Amin and I wrote. If you send me a personal email, I will reply with the actual full version of this, and it's in color, not the black and white, which is what you get if you buy the book. So.
So did you specify how you do the inactivation? Is it a guessing, or is it kind of you leave it up to them to do it?
Actually, if you read this, it really describes
Exactly how to do it.
pretty much almost exactly how to do it. We actually had some debate about how much we should describe that, because
Sometimes you don't describe to the coder, you let people figure it out.
Yeah. But we did do a pretty thorough job. And this was all on Qualcomm time, so it was kind of, I spent a month over in Switzerland with Amin sort of writing. Yeah, it was terrible. It was terrible. Okay, so complexity you can see is the, Reed-Solomon code versus Raptor. This is much faster. It stays linear as the size grows and the losses grow and so on. This is one of the main reasons why Raptor Q is better. So what this shows is the number of encoded symbols you receive beyond K. So 0 means you received exactly the number of source symbols in the original source block. And with Raptor code, we have this upper bound on it, which goes down sort of like a random GF2, a little bit slower, but essentially like a random GF2 code. With the Raptor Q, you get a much, much tighter error curve here. So 0 overhead, and we've tested this, billions and billions of trials with different error probabilities over all the different source block lengths. Yes, okay. And it at 0 overhead, it fails to decode only with 1%, and every extra symbol goes down by a factor of 100. So it really is almost like an MDS code. I'll just say one word. Spent a lot of time in the IETF actually defining the whole suite of protocols so I could incorporate the Raptor and Raptor Q into that. And that suite of protocols has actually been adopted into every broadcast service layer that I know of around the world, for mobile at least. including LTE broadcast. So it has this suite of protocols that we defined in the IETF, and it's used for broadcast file delivery. But interestingly enough, it's also used for streaming services. So you're using file delivery protocols for streaming in the, over the LTE broadcast system. And one other thing that we did a lot of work on in MPEG was this DASH suite, Dynamic Adaptive Streaming over HTTP. And that is also being adopted into LTE broadcast for doing the streaming. And interestingly enough, the reason for doing that is because that's what's being used for streaming over the internet at this point. How many of you think you've used Dash before? Okay, how many of you watch Netflix? How many of you done a YouTube? Okay, how many of you now think you've used Dash before? Okay, so that's really what everybody's been converging to. This and HLS. HLS is the Apple version of what they've defined for adaptive streaming. Dash is the one that we have a consortium of companies around that kind of have converged to that. And hopefully one day everybody converges to one solution, but we're almost there. But anyway, the reason for doing this here is because they see it here and they want to have converged services, right? So you can do something over broadcast and also do it over HTTP and have a system that goes back and forth. So how much time do I have now, Tom? You're supposed to. 8 minutes, all right. Okay, so this part is why fountain codes. So one of the things that the Raptor Q are nice because they can deal with large numbers of source symbols and do efficient encoding, decoding. But is this fountain property really important? So I'm not going to convince you totally, but I'll maybe give you some ideas behind why it might be interesting to have that kind of thing. So this is what I talked about before, this LTE broadcast system. This, by the way, started back in 2006 for the original standard, and we were all hoping that was going to take off. It didn't. So now there's a new round which has a little bit more promise of taking off. I know there's some deployments around the world at this point that are starting off. But this is really a cellular broadcast solution, LTE broadcast solution for streaming and delivery of popular content and really offloading that content from the HTTP internet. And so here's an interesting application of a Raptor Q or fountain code in general idea for using this service. So the idea is you have an original content, and just for a play example, I have 10 source symbols there. And now you only broadcast the repair symbols. You don't broadcast the original source. You just broadcast the repair. And why do you do that? Well, you've got some device which, if it receives at least 10 symbols here, it can decode, right? Then you're happy. But what if it receives less? Now what do? Do you schedule another broadcast session? Do you throw all this data received over the broadcast network away? Or you do something else? Well, really what you do is something else. So in this case, you can't decode if you receive less than 10. But the idea is that you have the same content available over the internet, over HTTP, right? And so this device only received 5 repair symbols. This one received 9. This one received 7. So what do? Well, what they can do is this first guy is missing 5. It just makes an HTTP request for a prefix of the content that's equal to 5 symbols worth. Right? So if symbols, say 1,000 bytes, it asks for the first 5,000 bytes of the content, receives that, treats it as source symbols, and decodes. The next one needs 1 byte, 1 symbol of content. But it can ask for the same thing that the first one asked for, just a prefix. So it asks for a little bit less, and so on. And so what you get here is this really nice feature that even though these guys receive different symbols here and different patterns and different amounts, what they need to do is only ask the HTTP edge cache server for a prefix of the content. And that's really good for the HTTP infrastructure, because asking for the same content again and again in the cache on the edge is really good for cache performance and really good for recovery properties. It also means they don't have to store the entire file on the edge. They're just a portion of it. The longest prefix is enough. Let me give you another quick example. I know I'm going to get kicked out in a second. How many seconds? 5 minutes, okay. So similar examples, so you have a content package which you're trying to deliver, which consists of media content A, B, and C, and I just made them all the same size, so they're each 10 symbols in size, so there's 30 symbols total. And now let's suppose through one way or another, device 1 has A and B, device 2 has B and C, and device 3 has A and C. So I can use the same solution as before, but now I'm going to broadcast the repair symbols. In this case, I'm only going to, for example, broadcast 10 symbols, which is much shorter than the total package, right? But those, and let's suppose there's no loss in this case, so all these devices receive these 10 symbols, right? But now you see they can all decode, right? Because they've got all but, because it's a systematic code, these are symbols of the original thing. These are different symbols of the original content, and these are a different subset of symbols. So combining those with repair symbols, even though they're the same repair symbols, they can all decode. So this gives a nice, by the way, this idea was from Jack Wolf and Amin Chakravarti from a few years ago. So it's a very cute, nice idea of how to use this thing. So the last thing I wanted to talk about, and I know I'm kind of running out of time, is supposed to be a practical session here. So I brought a real working demo, and maybe Lawrence can come up and get it to work. So Lawrence is actually the guy who not only wrote all the Raptor code, by the way, but he also implemented this application. You're going to let me, you trust me to hit the right one? Okay. Okay. Okay, good. So what you see here, I'll tell you what it is in a second. So you see here is just a movie, and we actually, this is just free content, so there's no licensing rights here, thank God. But you see when I hit the seek button, how fast it started again? And if I do that again, I'll seek over here. Immediately comes up. If I do seek back here, immediately comes up. If I do seek here, comes up immediately. So that's the point. The movie is not stored in its original form. What we did for this was we broadcast, simulated broadcasting just repair symbols. So what we did is we sent the repair symbols to that device over UDP. We actually induced loss on those symbols just to make it realistic, 20, 30% loss. And then what we did is when receiving them, we just wrote them to the SD card, the original repair symbols, not the decoded content. And so as they come in, you fill up your SD card. And then when the player wants to play back the media, it goes back and reads the appropriate portion where you seek to, and just reads in those symbols and decodes on the fly and sends it to the player and plays it. So what you were actually seeing there was Raptor Q in, let me go back to the previous. Do I have the? Yeah, so here's what the parameters were. So it was the 91 megabyte file. It was partitioned into 10 source blocks, about 9 megabytes each. But those were further partitioned into subblocks of about 223 kilobytes each. So the symbol size is 36 bytes, and there's about 6,300 source symbols in each time we're doing the decoding. So what it was decoding when you seek was a subblock of 223 kilobytes. Each symbol is 36 bytes, and it's got 6,300 symbols, and it's doing that in essentially real time. So you really can't tell the difference between doing this and when you've... So what's the advantage of this? So typically what you do in a broadcast, you send the whole thing interleave because you're trying to get the best protection against packet loss, right? So you send this whole thing mixed up, interleaved as much as possible. And then when you receive on the device, typically what you do is a post-processing step where you bring the whole thing in the memory, decode it, and write it back to the flash drive, right? So there's two problems with that. First of all, it's a long time after you receive until you can play it back, because this post-processing, if it's a big file, it takes a long time. And second of all, you're writing twice to the flash. And as we heard earlier, these flashes don't have a long life to them. So the less you write to them, the better. If you read, that's not a problem. But if you keep writing to it, that's a problem. So what this does is, as soon as you deliver as soon as you finish the broadcast delivery, the content is accessible. And actually, on the fly, you're only decoding the parts the end user is ever consuming. So you can do this all in very fast, kind of real time. OK, I think I'm out of time. Thank you.
Any questions? Maybe we have time for, and we have some slack here. So, any questions?
I had a detailed question.
Yes.
Are you using the systematic Raptor code and then sending just the parity symbols for it, so you
Yes.
can send the systematic later?
Yeah.
Okay.
You never send the systematic.
Well, in some of your applications, like you went and requested the system parts of the system.
Yeah, because
You have to use the systematic code for that to work, right?
yes, absolutely, you need the systematic code for that to work. For those examples I gave, where one guy has A, B, and that was, so what you're doing is you might think that those other files were downloaded over the internet using standard HTTP, right? So that part of the infrastructure doesn't have to know anything about coding. The only part you're using coding is when you broadcast it. But you can combine the broadcast with normal HTTP internet services in a kind of seamless way without the internet ever knowing about coding.
I think you had a question first.
Okay?
You mentioned using Gaussian elimination when DP is stuck.
Yes.
How do you still get linear time?
So you do some, that's what this inactivation decoding is. You kind of set aside an equation if you can't solve and say, OK, I'm going to solve that later. And you just keep going. And using belief propagation. So you sort of set one aside. So you had a degree 2 guy. Say, oh, I can't solve because I need a degree 1 guy. Set one of those guys aside and keep going. Because now you got a degree 1 guy. And then you kind of keep going and you eliminate the other part and you solve this part here and you go back. And so it's a little more complicated than.
I think the point is that the typical size of that is bounded by the square root of the size.
I see. So you don't pay the...
Yeah, so the number of inactivations you do is limited. Yeah, you don't keep... you still need it to be, most of the time, belief propagation to work. But when you get stuck, you don't get stuck. You just keep going.
You're only left with, say, a square root,
Yeah.
square root number of...
Yeah, yeah. In fact, more than analysis in reality.
Well, you tried that in the constants.
So why did they insist on systematic?
For lots of reasons, and I agree with them completely at this point. At that point, I was really pissed off. Yeah. But at this point, because nobody likes something which they don't understand is maybe the main, right? But then it turns out there's all these other applications and ideas you can use if you really have the systematic part. So it really makes sense.
Yeah, including backward compatibility.
Yes, that's in one. If some receivers don't have a decoder, but some do, you don't want to punish the ones that don't, as an example.
Okay. Okay, thanks, Mike.